Okay, so this was actually a request. So someone said I had made a video showing how to calculate the electric field due to multiple charges, and the question was, what if I have a charge I want to model moving near that? So I kind of made a situation here. Let's take a dipole. So a dipole has a charge of minus q, let's call that big Q, and plus q, and it's separated by a distance s, and this is going to be centered at the origin. So what is this charge up here going to be like? Now, the first thing I need to do is to assume that these two charges are either very massive and don't move, or they're pinned down. Okay, so I have up here some other charge, lower q, and has a mass m, but those things can't move. So how do I model the motion? Well, the number one step is to find the electric field. So I'm going to calculate the electric field. I'm going to calculate the electric field due to this charge. I'll call this E plus, and the electric field due to that charge, E minus, as vectors. Okay, now to do that, I need this vector. I'll call this, let's call this R1, and this vector R2. So I'm going to have to find those two vectors and then calculate the respective electric fields, calculate the total electric field, and then I can calculate the force. F net is going to be Q times E net. So this calculating the net electric field is what I did before. Okay, so but now I did that part. But then how do I know how it moves? This is where we're going to do a numerical calculation. So we're going to break this into tiny steps. So let's say this has a force on it like this. This is the net force. I'm just picking something like that. If I know the momentum of this charge, then I can find the change momentum. So that's the first thing I'm going to do, is start with initial conditions. So that means what's my initial momentum, what's my initial position, then that's really all I need, and time is equal to 0. And then I'm going to break this into small time steps. Let's say dt equals 0.01 seconds. And during that time interval, I can calculate the change momentum by doing this. P2 is P1 plus F net delta t. And this is true. I switched from dt to delta t. I'm sorry. This is true. Okay, I can do that. Then I can use this final momentum to update the position. R2 equals R1 plus P2 over m, which is the velocity, delta t. Up here, I guess I need to add another step. Before I use this, let's say 1a, calculate F. I need to find that net force. So I'm going to calculate the force. I'm going to use that to update the momentum. I'm going to use that to update the position, which is going to change the forces. So I need to go back up here and redo it again and repeat this over and over and over again. And that's what I'm going to do. Of course, if I want to model the motion of this, I don't want to do 1,000 calculations on paper. So I'm going to use a program to do that. So I'm going to switch over to Python. We're going to do this on the computer. And then I don't know how well it's going to turn out. I don't know the values for these. I'm going to have to pick some values for the charges, the separation distance, and the mass and that charge, and the initial conditions. But let's just see how it goes. So let's head over to the computer. I'll meet you there. Okay, so here we are I'm using Trinket for my Python, and I've gotten a jump start because I just wanted to get things working. Okay, so I apologize, I didn't wait for you, but here we are. So let's just go over what I have so far here. This is the Coulomb constant. This is the separation between the two charges. This is the value of the charge, and then I have the two charges right there, Q1 and Q2, and then I don't know, I called it a charge. I shouldn't have. Let's call it a ball. I'm gonna call it a ball. And then I put it, let's move it. It's a little too far away. Let's put this at 3, 4. Let's see what that looks like. Because it's way up there, and I made it a little bit smaller. Okay, so there's my charge. I should probably, let's put it at 2, 3. 2, 3. And I just picked a location. I don't know what I'm doing. Okay, that's good. Now I need to find the mass and the charge of this. Okay, so this is actually going to be difficult. And I think I need to do, let's call this Q over M. Okay, so this is the charge per mass ratio. And let's just start with this as an electron. Okay, I don't know. It's just going to be an electron. So Q over M for an electron is going to be negative 1.6 times 10 to the negative 19th divided by the mass of electron, which I cannot remember off the top of my head. I'm looking it up real quick. Mass of electron. I think it's 10 to the negative 27th. Mass of electron is, 9 times 10 to the negative divided by 9.1 times 10 to the negative 31. So it's an electron. Again, this may be horrible. I don't know. So that means that the Q, I don't know why I did this. So Q is going to be equal to, okay, let's not do that way. Let's do this. Let's just do ball.Q equals negative 1.6 times 10 to the negative 19th. And then I could set the mass. So ball.M is going to be equal to, I can't do that first. Ball.M is going to be Q over M. So let's see, if I want the mass of, I would take ball.Q divided by ball.M, but by Q over M. I know this is dumb, but this way I only have to change one parameter. I apologize. Okay, I need the other thing. I need the initial momentum. Ball.P equals ball.M times vector. Let's just start with it from rest. We can change this. Okay. I think that's good. Okay, so the first thing we're going to do, let's go ahead and start a loop. We need t equals 0 and dt equals 0.01. And again, I don't even know if this is going to work. It's going to be a good value. And I don't know how fast things are going to go, so I'm just going to say while t is less than 10 and run it, and let's see what happens. So rate 100, this tells the thing not to do more than 100 calculations per second, so it'll work in real time. Oh, let's go up here. My ball, I want to add a trail. Make trail equals true. But you got to spell true. Okay. Now the first thing, just like I said before, I need to calculate the force. But in order to do that, I need to calculate the electric field. I could make a function here, and it'd be really nice and it'd look prettier and stuff like that. But I'm not going to do that because I want to make this as simple as possible. So I'm going to first calculate R1. R1 is going to be the vector from charge 1 to the ball. So this is going to be ball.pos minus q1.pos. R2 is ball.pos minus q2.pos. So those are those two vectors. Now I can calculate E1. That's going to be the electric field due to charge 1. It's going to be K times Q1. I can just calculate the force. Let's just calculate the force. F1 is K times Q1 times Q1.Q times ball.Q times norm R1 divided by mag R1 squared. So remember, the equation for the electric field due to a point charge is K Q1 over R squared, but I need to have that norm 1 is a unit vector pointing in the direction of R, and that makes this whole thing a vector answer. If you didn't do that, you'd get a scalar and you wouldn't be able to do anything. Okay, let's do force 2. So I just copy that, change this to 2, 2, 2, 2. And then F, this is called F, is F1 plus F2. You could do that all in one line if you wanted to, but I didn't do it. So now I calculate the force. The next thing I'm going to do is update the momentum. So ball.P equals ball.P plus F times dt. And then I need to update the position of the ball. Ball.POS equals ball.POS plus ball.P times dt divided by ball.M. Now I need to update the time. And I have a feeling something's going to break, but you never know. You never know if things are going to work or not, right? So that's why you just have to do it. So let's run this and see what happens. I'm kind of scared. Okay, so it just exploded. I think let's just make this time a lot smaller and see what happens. Rate. Well, this is fine. Let's do that like that. Okay, let's make the mass greater. So let's say the ball.m is, let's say, I'm just going to pick a mass. Let's say ball.m equals, let's say 1 times 10 to the negative 10th. I think that's my problem. Oh, now I need to do, it's not doing anything. Let's put this back. I think that's too big. Now it's not doing anything. Let's make it 10 to the negative 15th. Nope. 10 to the negative 18th. I'm just guessing here. I should have calculated something before. Oh, there we go. It worked. Okay. So that's pretty cool. Let's do this. Let's print the final time, which is 0.1. I already knew that. Let's print the final momentum. Ball.p divide the ball.p divided by ball.m, because that way I'll know what a reasonable velocity would be. So it's going pretty fast. Okay, this now up here, let's give it some initial velocity, because let's let this run for a little bit longer, for a second, and I'm going to give it an initial velocity of, let's say, 1, -2. Okay, so that's cool. What happened was it got a little too close to one of the things and it just exploded. That's fine. I'm fine with that. Let's just increase this to 3. Maybe we can get a kind of an orbit. Okay, that's pretty cool. I think things are working here. I do know, I remember one time, okay, that's cool. That's exactly what I wanted. Okay, now, I don't know that everything is working right. You may want to look at conservation of energy and see if your calculations are doing a good job, but I'm just getting you started here. Now, the thing that I remember is, I think that if I start the charge right here on the y-axis, I think it oscillates back and forth. So let's do that. So let's give it a 0 momentum. I'll just say 0, 0, 0. I'm really kind of excited that this worked at all. And then put the position on the y-axis right there. So it starts at right here on the y-axis, and I'm going to let it go. Yep, that's what it does. It oscillates back and forth. Isn't that awesome? Come on, that's pretty awesome. So why does it do this? Up here, the electric field due to these two charges is to the left, right? But it's a negative charge, so it pushes it this way to start speeding up. But then as it gets over somewhere like around here, the electric field is pointing that way, which makes it turn into a circle. And then the opposite thing happens down here, and it oscillates back and forth. This is a really cool classic problem. But I just wanted to show that. Oh, and also this is in 3D, and you can rotate it around. And I think that the thing's working fairly well because it goes back and forth over the same path as it should. If you want to plot conservation of energy and stuff like that, that's a great problem for you to do. I'm not going to do that because this video will go on forever. But there you go. I answered the question. I modeled the motion of a charge near two other charges, and I did it, and it worked. Okay. We'll do some more physics later. I'll talk to you later. Wait, I said later twice. Okay, let's do this. We'll do some more physics. I'll talk to you later. How about that? Okay, bye.